Okay, so hi everyone. Welcome to another MLFL. And this week I'm very excited to introduce Ankur Parikh. Ankur is a senior research scientist at Google Research in New York City, and he's an adjunct an adjunct professor at NYU. Ankur's research is in natural language processing and machine learning, and recently he's focusing on high precision text generation. He received his PhD at CMU, and he received a Best Paper Runner-Up Award at EMLB 2014 and a Best Paper Award at ISMB 2011 in Translation Bioinformatics. On a more personal note, I was an intern with Ankur in summer 2019, and we had a lot of fun working on model extraction. A number of these projects were, I think, in progress at that time, and I'm really excited to see what's come out of them. So yeah, as I said before, if people have questions, leave them on the chat or raise your hands, and I'll interrupt Ankur accordingly. And yeah, without further delay, let's get started. Ankur, over to you.
Okay, thanks everyone for having me. So yeah, feel free to ask questions during the talk, so that way, otherwise it gets lonely just talking from my bedroom. Okay, so this is joint work with Thibaut, Ran, Shuja, Sebastian, Sashi, Manal, Buwandi, and Dependent, all at Google Research. And so this talk is going to be about neural text generation. And in recent years, neural text generation has become surprisingly fluent, especially as you build bigger and bigger language models. But what we've seen is that even though it's very fluent, it's still prone to hallucination, which makes it unsuitable for real-world applications. And I'll give some examples of hallucination on future slides. But basically, it means that the model is producing things that are fluent but are unrelated or unsupported by the source content. And we're going to explore this challenge kind of in three angles, from models, from data, and evaluation. And we'll show that kind of all three are important and shed different light on this problem. So the problem of hallucination is that basically I have some source. So this is a conditional generation test. This is data to text, where here, given this source, which is a Wikipedia info box, the goal is to generate a one-sentence description about a person. And you can see that this person is Frank Lino, and they were born in October 30th, 1938 in Brooklyn, New York. And the neural baseline says these things, but then it also claims that Frank Lino was a criminal defense attorney, which is not supported by the source, and which is not true. And this is a common problem in neural generation systems, not just in data to text, but in summarization and other problems as well. But we're going to focus on data to text for a lot of this talk because it's easy to evaluate kind of the accuracy of a neural generation system by comparing to a source table rather than kind of a long document or a set of documents that you would do in summarization, for instance. So hallucination has three kind of causes from our studies. And so one cause is data, which is that in many data sets, the target just contains information that cannot be inferred from the source due to how the data was collected. And so, for instance, here about Frank Lino, the gold reference is the first sentence of the Wikipedia page about Frank Lino. And you can see it has a lot of information about Frank Lino, about how he was in the Bonanno crime family and how he later became an informant. But none of these things are actually in the source table. And so when you train a model on this reference, it's kind of encouraged to hallucinate. And this can make it confusing. And you may ask that, well, if I removed all of these irrelevant parts of the gold reference and I trained the model on clean data, would the neural model still hallucinate? Or is hallucination just about data noise? And we'll answer this question in this talk. The other kind of cause of hallucination is how models are evaluated and how this kind of encourages a certain type of hill climbing in the community. So BLEU is kind of the most common metric for text generation. And BLEU, unfortunately, does not really care about faithfulness or kind of accuracy. It mostly just cares about coverage and fluency. So here, this table is about Michael Dahlquist. And the reference is that Michael Dahlquist was a drummer in the Seattle band Silkworm. And we can see that candidate 1 has the highest BLEU score, even if candidate 1 is wrong. Candidate 1 claims that Michael Dahlquist was in a California band, Grateful Dead. But there's enough word overlap between Seattle band Silkworm and California band Grateful Dead that Blue really likes this. And also, it's about the same length as the reference, which Blue also really likes. If you produce a shorter candidate than the reference, then Blue will really penalize you. So that's why Blue does not like candidate 2, even though candidate 2 is actually correct and would be preferred as an output of a neural generation system over candidate 1, which is wrong. Candidate 3 is even better than candidate 2 in some way because it has some extra information from the table, but it's not in the reference, so the model isn't really getting any credit for producing extra correct information. And finally, along with data and eval, models are, of course, a problem. When you have, for instance, noisy data, and then you use maximum likelihood to train your model, you're basically encouraging the model to kind of hallucinate because you're giving it the previous gold tokens and asking it to kind of do its best to predict the next token. And so it's basically encouraged to guess to bring down the loss. So we've been doing a lot of work in this space since 2018 on kind of data eval and models, and also kind of orthogonally on MT for multilinguality. In this talk, I'm going to focus on these 3 works, one from data, one from eval, and one from models. Does anyone have any questions before I continue?
I think we can continue. There's no hand raise or chat.
Okay. So the first topic I'm going to talk about is a data set that we collected that's appearing in EMNLP this year. And it's also publicly available at this link. So our data set is designed to present a controlled generation task that we believe will be useful to study high precision text generation and hallucination in modern generation models. And so the task it presents is as follows. You're given a source, which is a table, a set of metadata about the table, and a set of highlighted cells. And the target is to produce a 1-sentence description of these highlighted cells in the context of the larger table. So here, for instance, this table is about Robert Craig and his NFL statistics. And we can see that the table has some kind of complex structure, like rushing is kind of a subheader for these multiple columns, and so is receiving. And there's a set of cells highlighted, which are the years that Robert Craig played, and his total number of rushing yards and receiving yards. And the target sentence that the human has provided is that Craig finished his 11 NFL seasons with 8,189 rushing yards and 566 receptions for 4,911 receiving yards. And so you can see that part of the sentence description is supported by the table metadata, like Craig and NFL. Part of it requires inference over the table structure, like you would count 1983 to 1993 to conclude that he played 11 seasons. And some of it is about copying information from the table along with the row column headers, like here. And so I want to kind of give some motivation of why we built this and what motivated us to build this. And the main reason is that many data sets like Wikibio and RotoWire contain a lot of noisy references, which makes it difficult to study hallucination, as I mentioned, because it can be unclear if the hallucination is caused by the noise in the data or the modeling shortcomings. And another option is you can ask annotators to write sentences from scratch, which don't hallucinate. But these will typically lack variety. So for instance, if I got an annotator to just write a sentence about Frank Lino, they would likely just say, Frank Lino was born in October 1938, and he's from Gravesend, Brooklyn, New York, United States, or something like that, which won't kind of give us the nice kind of inference that you see here with 11, for instance. Furthermore, another shortcoming that a lot of generation tasks have is that they're often not super well defined. For instance, in summarization, in a way, some of the open-endedness of summarization is challenging, but in a way, it's difficult to evaluate because if you ask annotators, write summaries, they may find many different parts of the document or the source that are relevant, right? So this is the RotoWire data set. We're here given a table about a basketball game. You need to produce a summary, right? And on the right, you can see that the model, all the red is all the hallucination that a neural model produces. But if I compare kind of the rouge or the blue score from the gold to the ground truth, it's difficult to evaluate because I could have definitely just picked different facts, right? Instead of talking about, Tyler Johnson and Dwight Howard, maybe, I find it more interesting to talk about, some of the other players that were important in other ways. So on the other hand, you can also define a task in a very constrained way, right? I can give you some sort of fully specified meaning representation, like WebNLG, which is like kind of like a semantic parse or something, and then you just verbalize it and produce a sentence. But that's not really challenging for modern neural networks. It's very if you give a modern neural network a kind of fully specified meaning representation, it's very easy for it to make a fluent sentence out of it. So ToTTo, we tried to design it to be novel in two ways. We tried to make the task design so that there's a controlled generation task where you get the set of highlighted cells that gives you some guidance of what to generate, but there's still some challenge required by the model on how to do inference or kind of interpret those cells in the context of the larger table. And then our annotation process, basically, we take naturally occurring sentences on Wikipedia, which are very interesting language and interesting linguistic phenomena. But then we get annotators to revise these sentences so that they're faithful to the table, which removes the data noise and provides for kind of a clean data set. And we'll see that our data set has 120,000 training examples, 7,500 dev, and 7,500 test, which we think is a sizable contribution, hopefully. So the way we collect the data is that we basically get some tables from Wikipedia. And you can see that they're about different topics. And they also have different structure. And then we use heuristics like word overlap or hyperlinks to find sentences that may be related to the table. So for instance, this table is about Gabriel Becker. And we found a sentence. After winning the German under 2,300 meter title, she was selected to run in the 1995 World Championships and other things. So what we see is that this heuristic sentence is very noisy, and it's not a suitable generation target. The phrases that are highlighted in yellow are things that are just not supported by the table. The table doesn't talk about her winning the German under 2,300 meter title, for instance. And furthermore, there's some pronouns like she, which make the sentence not standalone. So it's not really something you would ideally like to replace the pronoun with the proper noun. So what we then do is then we have an annotation task where the annotators first highlight cells that support the sentence. So in this case, they've highlighted 1995 and World Championships because those are mentioned in the sentence. And they've also highlighted 100 meters and 4 times 100 meter relay because it says that she competed both individually, which would be supported by 100 meter, and in the relay, which is supported by 4 times 100 meter relay. Then they iteratively revise the sentence so that it's faithful to the table and standalone. So the first step they perform is deletion. So here they basically delete all the phrases that are not supported by the table or the table metadata. They then perform a decontextualization step where they would replace pronouns like she with proper nouns like Gabriel Becker to make the sentence standalone, which is shown in the orange box. And then there's kind of a final grammar correction step to make the sentence nice and fluent again. And here you can see the annotator made a minor change by deleting a word. So this overall gives us a sizable data set of 120,000 training examples. You can see that there's quite a bit of tables. There's about 83,000 tables, and the target vocabulary size is 136,000 because our data is kind of open domain on Wikipedia. Another interesting aspect is that the tables are actually quite large. You can see the median number of cells is 87, which would make the task not well defined if we just said given the table to generate the sentence, because you wouldn't know at all which cells to mention. But you can see the number of highlighted cells is 3, and it's much smaller, and that gives some control as to what to generate in the task. And furthermore, with our annotation process, you can measure annotation agreement at each stage. So after deletion, for instance, the blue between annotators is 82.9, and it kind of gracefully degrades as you do more revisions, which is as you would expect.
So Ankur, I had a clarification question here.
Yes.
So you have multiple annotations per training set example?
Only in dev and test.
Okay. Okay. Got it.
Yeah. Sorry. So the training set is single way, but the dev and the test are 3-way.
Okay.
Then we did some kind of manual analysis to see the different phenomena in our data set. You can see on the left, there's the overall topic distribution. So about half of it is sports and countries, and the other half is more rare topics, which can kind of give it the challenge to the model, as we'll see. And even sports, sometimes, even if it's very common, it can be challenging because a lot of the numerical reasoning and things like that are related to sports. And on the right, we basically took 100 randomly selected examples and manually annotated what type of phenomena we see. So for instance, we saw that 21% required reasoning, which is logical, numerical, or temporal. 13% required comparison across rows, columns, and cells. We then ran some baselines to kind of show how current models perform on this data. So we took one large pre-trained model, which is BLEURT to BLEURT. It's basically a transformer encoder decoder that's where the encoder and the decoder are initialized with BLEURT checkpoints. Then there's pointer generator, which is a sequence-to-sequence LSTM model with a copy mechanism that's very popular in summarization and also for data to text. And then we took a specific data to text model that uses content planning that was designed for RotoWire. And we have 3 metrics. I mean, we have 2 metrics in the paper, BLEU and parent, which is a special metric we had developed for data to text. And on the leaderboard now, we also have BLEURT, which is a learned evaluation metric. And you can see that all the systems currently rank the 3 baselines the same. They rank BLEURT to BLEURT the best, followed by pointer generator, and followed by the specialized content planning model.
So we have a question.
Yes.
Mohit, do you want to unmute yourself?
Oh, yeah, I was just wondering if you considered trying to increase the percentage in your data set, like artificially, of the maybe more interesting cases where they have to compare values or columns or do some sort of reasoning, because those, I mean, 21% or whatever is a lot, but it could be higher, and maybe that's...
Yes, it could be. We did not do that. We did do some skewing to make the data set harder, but we decided to do it based on topic. Or so basically we removed, if you had certain rare column headers in the dev and test set that were not present in the training set, we removed those examples from, I mean, sorry, certain column headers that were present in the dev and the test, we removed them from the training set to kind of get a out of domain type of dev test split, which makes it harder in some way because the model can't memorize what certain things that it's seen in training. But I agree, another angle to make it harder could have been to somehow use heuristics to upweight some of the examples we thought were reasoning based. Yeah, but I think it's kind of a trade-off because a lot of the ones that are reasoning based are kind of sports, so you will lose the topic diversity. And a lot of the ones that are interesting topics are interesting because they're kind of rare, but not because they have a lot of reasoning, for instance.
I see, thanks.
I had one more question. So I was wondering how you use BLEURT here, but if you're going to discuss it later, it's fine. Like I was wondering whether you use...
I did not do a custom. I had intended to do a customized way, but I think it's a little bit tricky because we have multiple references for dev and test, and BLEURT typically takes a single reference. Mm-hmm. I just used the BLEURT out of the box on the candidate and in each reference, and then I took the average.
Okay, thanks. Yeah.
I also tried max, and it increases the scores, but it didn't seem to be relatively different. So.
I see. Okay, thanks.
So then we did some human evaluation. And so basically here, this is we compare the top performing model to an oracle. So the way we compute the oracle baseline is that the dev set or the test set has 3 references for each example. We hold out one of the references and pretend it's a model prediction. And the annotator compares it to the other 2. And this gives us, and so the annotator says that the oracle is 99.3% fluent and 93.6% faithful, which we think is quite high. And then the top performing baseline we see has lower fluency and significantly lower faithfulness. The BERT model has only 76.2% faithful, so it's hallucinating a significant fraction of the time. And this answers kind of one of our key questions that we kind of were motivated by when building this data set, which is that do neural models hallucinate even in the presence of clean data? And it seems to be, with current models, the answer is currently yes. And I have some hypotheses of why this is when we look at some of the mistakes. So one type of mistake we generally see is that models struggle with rare topics that they haven't seen in the training data. So for instance, like this table, there's probably not that many training examples about microdrives. And so it doesn't really understand the terminology. And so the model just says there were 512 microdrive models in 2000, 1 gigabyte, which doesn't make any sense. But the reference is quite good. It says, a second generation of microdrive was announced by IBM in 2000 with increased capacities at 512 megabyte and 1 gigabyte. And you can see the reference also has some interesting reasoning language. It says second generation, which you would infer from the table structure. It says increased capacities, which you would also which you could infer from looking at the previous year's capacities.
So we have one more question.
Yes.
Nadir, do you want to unmute yourself?
So in the previous slide, you were showing that the BERT model, even though it was the highest baseline, seemed to hallucinate. I was just wondering, could we really call the BERT model clean data since it's been pre-trained on a large corpus of information outside of your data set?
Oh, sure. Maybe, yeah, sure. It definitely has been pre-trained on other things. Yeah, I mean, I think that's a fair point. But I also think that the models that are just trained on the data perform worse in general. So.
Okay, so the other 2 models are not with any pre-training, are just on the data, and they also have faithfulness issues?
They also have faithful. I didn't run a rigorous human eval, so I can't tell you the exact percentages, but I think if you look at them, you will also see that they struggle. Yeah. I think the reason for it is not so much. I mean, I think pre-training definitely does have a hallucination effect, but the model is also good. Like it also gets better at guessing right when it's pre-trained. So I think it trades off like that. I think the reason it hallucinates a lot on clean data is because a lot of the times, even if the data is clean, it still contains inferences that are not always easily apparent from the table, right? So if I see second generation here, if the model sees that, maybe it doesn't bother to learn about the table structure that, oh, I can infer second from 2019-99. It's just easier for me just to put any, number there, or any adjective. And I think those are types of things that we see.
So we have one more question. Amaya?
Yes.
So my question was basically about the faithfulness chart that you showed on the previous slide.
Yes.
Is faithfulness covering all the facts in the references, or is it ensuring that no hallucinated facts are added?
Sorry, so faithfulness is precision. So it is, the model is faithful if all the information that it states is supported by either the table metadata, or one of the references.
Okay, thanks.
The coverage is also lower, but the coverage numbers are a little bit difficult to show, but they're in the paper. But basically, we take the model and we ask the annotator whether they think that the reference is more or less informative. And we generally find that the annotator prefers that the reference is more informative than the model prediction.
Okay, thanks.
But I didn't know exactly how to visualize that here, so I didn't show it. Yeah. And I think the way you also talk about, since you're talking about coverage, I think the way we talk about coverage is also kind of complex, right? So I think this is an example where if you say that you have full coverage if you mention all the cells that are highlighted, then this model has perfect coverage, right? So it says Travis Kelce finishes the 2012 season with 45 receptions for 722 yards and 8 touchdowns. And so it's mentioning all the facts that are in the table. So in a way, it's covering all the cells. But if you compare it to the reference is much more informative, right? So the reference says in Travis Kelce's last collegiate season, which you can infer from seeing that 2012 is the last year that he played. He made personal career highs, which you can also see from kind of comparing 45 and 722 to the other numbers from the previous years. Yeah, so I think that's why if you look at the paper, we report both coverage in terms of percentage of cells covered, as well as kind of this comparison that whether the prediction is more informative than the reference or not. Are there any other questions about our data set? We encourage you to try it. And if you have questions or suggestions, you should feel free to contact us.
Ankur, I had a question.
Yes.
So in the last slide, for example, the reference. So in the reference, the table is contextualized within the text. For example, in this, you see the year 2009, 11, and 12. And in the reference, you have last collegiate session. But that's not necessarily right when you just present the table, right? Because you could have just these 3 years presented for some reason, but it need not be the last year of this player. So
yeah, I mean, I think what you're asking is kind of this is the problem with all kind of entailment, with the definition of entailment, right? Like, I think that's also true of other, I think we kind of assume that this table is kind of the world.
Right, exactly.
So if it doesn't have, if he played in 2013, but it's not there, then, it's not considered like to be, supported.
Maybe it's rare enough to ignore this. So that's what I think.
I mean, you definitely see, I think you do definitely see cases like that. Mm-hmm. But I think the annotator is editing the reference so that it's totally supported by the table. So we're considering the table to be the world. So if you definitely see some rare cases, for instance, where the sentence may say that this is the second tallest skyscraper, but the table will say that it's the third tallest skyscraper because the table is not updated or the text is not updated.
Yeah, right.
And the annotator is expected to follow what the table says.
Yeah. Right. Thank you.
Yeah. Hi. Can I ask you some questions?
Yes.
Firstly, did you check how many of the words in the sentence which appears in the table has been highlighted in the table? Because I checked the first few examples from the ToTTo dataset. I found that some of the cells mentioned in the sentence annotation, but they are not highlighted in the table.
There are, I don't know the exact percentage. I mean, we looked at things kind of manually. Mm-hmm. There are definitely cases where the it's kind of subjective. So we definitely don't, I think the annotators are instructed not to highlight any row column headers. Okay. So you will definitely get all the column headers in the table title and things like that they're not highlighted regardless if they're in the sentence or not. So it's only the cells. Which might be the reason that you don't see that much, which you see less overlap if a lot of them are headers or titles. When it comes to the cell contents, they should, based on when we looked at the data set, it seemed that they should have highlighted everything, but sometimes they make mistakes and sometimes it's subjective as to whether something is important or not. I don't know if that answers your question.
Okay. Yeah, I haven't.
We can follow up on it offline. I think if you have some specific examples to show me, then I would be curious to hear about. I would be curious to hear about them and to see. I do see sometimes in the dev set you'll see that, because in the dev set there are 3 references. So there are 3 annotators. They chose 3 different highlights, and there are 3 references. So I randomly took one of the highlights to use for the input, and then took all 3 references. So you may see a case where in the dev set there's less alignment between some of the references because the highlighted cells only corresponded to one of them.
Okay. So during the annotation, did you first provide the possible cells which would be highlighted to the annotators, and then let them choose between them, among them? Or
no, they do it themselves. So I get the table and all the cells are clickable, except the headers, and they click on the cells that are relevant.
Okay. And also, for the faithfulness to the table, does that mean the content of the sentence should be very relevant to the table, or it also did you also consider whether the sentence is true according to the table content, entailed by the table? For example, for some sentence, it might be the total of the score of some year is the number, but this number didn't appear in the table, which requires the model to compute the sum and then generate this sum. In this case, you also need to check whether this number is correct or not.
Yes. So the annotators are supposed to do that. They're supposed to, it is considered that if the total is there, in this example, where did that example go? Here, 11 is considered supported by the table if they sum these cells, right?
Yes.
So now there is some subjectivity on what they should highlight, right? So some annotators just highlight, the first and the last tier. Some annotate all of them. There's definitely some differences in that. I think we didn't give them specific guidance on, because I think there's too many cases. So I think it's whatever the cells they thought would support 11.
Yeah.
Sometimes you will see that, yeah.
If for example, here there's a total row in this table. If there's not no such row in the table, and the sentence has the 8,189 as the sum, if the model didn't generate the correct number,
so it should be penalized. The reference. So in an ideal world, let's say the total row is not there.
Yes.
And the reference has 8,189. Sorry, the heuristic sentence. The annotator should highlight all of these yards, 725, 649, 1050. All of these, they should highlight all of those cells. That this is, and then the model in the end would be expected to be able to do the arithmetic. Obviously annotators are not perfect, right? So some of them may be lazy and just delete 8,189 because they didn't see the number in the table. But they're technically not supposed to do that.
Ankur, how are we doing on time? So I think we should move on and.
Yeah, I think we can move on, unless I think I saw one more question in the.
Yeah, but I think you have 2 more things to cover. So maybe we can take more questions at the end of the talk, unless there's some quick clarification over the next 2 parts.
That sounds good. That sounds good. I can go faster through the other ones. Yeah.
Okay. Yeah. Yes.
Okay. Thanks. Cool. I have until 1 o'clock, right?
1:05 technically. So yeah.
Okay. That should be good.
Yeah.
Okay. So what I want to talk about next is how to do eval, right? So we talk about how, let's say in the data set that we were discussing, there are different types of mistakes, right? Some of which are easier to capture with automatic metrics and some of which are not, right? So the first example, the prediction just doesn't make sense. It's about the NFL draft, and there's very little word overlap with the reference. So we would expect BLEU to be very good at that. But the second example is also incorrect, but it's only incorrect in 2 words. It's incorrect in the numbers that there are 6 Grand Prix races in 5 classes, not 8 Grand Prix races in 6 classes. And so it's incorrect, but the word overlap is high, which would make BLEU not sufficient. But even a general type of sentence similarity neural model would probably be sufficient, because it would be trained on some data, and it could probably look for these types of fine-grained differences. In the last one, both the prediction and the model are correct, but the reference is just much more informative. And so if we are looking for this type of criteria, it may, using a conventional sentence similarity model or entailment model may not be suitable. And so what we've been kind of, what we believe in is that when you want to do these types of fine-grained evaluations, learned metrics are kind of the easiest way to go, because basically you can take BERT, you can fine-tune BERT on some human ratings data that correspond to the exact type of quality you want to measure, just like you would a classifier, and then you'll get a learned metric. This has some problems though, and I think the main issue is that it's very brittle. And so you require a lot of fine-tuning data for every new data set and task. And you can say that is, that's how models work, right? But eval metrics, you would ideally like them to be a little bit more robust and more stable, so you don't have to constantly get like a lot of data for every new task or every new data set that you want to evaluate it on. So what we propose is BLEURT, which is a more robust learned metric, where we add an additional pre-training or mid-training step based on synthetic data that we hope makes the model robust to different types of trained test queues, and enables fast adaptation to other domains with only a few examples. And at the time we published this, it was state of the art on WMT and WebNLG. So we know that the synthetic data, the purple box is kind of the novel part. So that's the part that I'll focus on, where here we basically want to generate a lot of data, which is reference candidate pairs that resemble real reference and predictions, right? And so we try to simulate different prediction errors, modeling errors that a model would make by doing things like deletion or substituting phrases or adding repetition or things like that. And this is ideally the types of things that you would see. And this is not something that you would see in a paraphrase data set, for instance, or an entailment data set. So the strategy we use to try to get this type of data is we use BERT, and we randomly mask text, and we employ BERT to fill masks. So here we can see that if I mask, I bought mask milk from mask store, then it would probably put almond milk or something, and the truth might have been soy milk or something. And then the other strategy we try is back translation, where which is commonly used in the NLP community. We basically take the sentence, we translate it to another language, and we translate it back. And that creates some variance and kind of creates a noisy paraphrase. And then we compute a variety of easily computed metrics for a multitask objective on the synthetic data. So we compute BLEU between the synthetic pairs, Rouge, BERT score, entailment, the back translation probability, and things like that. And then that's what we use as our synthetic data training. And then we have some human ratings data to fine tune. And so I'll just show results on WMT 17. But the other results are kind of similar. So basically, Scent BLEU, CHR, F++, Beer, Mover score, and BERT score are other learned metrics. Now there's definitely more, but these were the baselines when we submitted the paper. And then BLEURT minus pre-training is if you just naively take BERT and fine-tune it on ratings data. So you see that alone gets kind of state of the art. indicating kind of the power of having an end-to-end learn metric over doing something like BERT score, where you take BERT embeddings and kind of use word overlap to compute a number. And then BLEURT, where we have the synthetic mid-training, it gives another 2 gain in Pearson correlation. I think the pre-training or the mid-training shows a bigger difference when we try to do some robustness experiments. So here we make a synthetic scenario where we, which is shown on the left, where we basically skew the data set. So the training set is skewed toward lower ratings. So it's skewed toward lower performing models. And there's a little parameter called a skew factor, where you can see 0 is the IID case. And then when you go to 3, it's like the training set is very left skewed. In the test set, we do it analogously. We skew it toward higher ratings. So here, the test set, as you keep increasing the skew, the test set looks less and less similar to the training set. And this is some simulation of maybe that you would train on models from previous years which perform worse, and then you would want to test on models in the future which might perform better, for instance. And we see on the right that BLEURT, without the pre-training, when you just take BERT and you fine-tune it on ratings data, it's not very robust to this type of skew. So you can see that the kind of the light blue to dark blue is the performance degradation as you increase the skew. And red is BERT score and green is blue, which you can see are relatively more robust. On the right, though, you see BLEURT with the pre-training. You see that for most of the skews, except for the really extreme skew, that it's actually very robust. So all the bars are kind of near the top. Only in the extreme skew case, which is the darkest blue, does it degrade considerably in performance. And here we also see results on WebNLG. So here, this is kind of our fast domain adaptation experiment. So here, basically, I think WebNLG, you can think about it in 2 ways. You can either split by the system. You can hold out certain systems in training and use them in test, or you can split by the input and remove certain inputs in training and use them on test. But regardless, we can see that we start. Let's take the bottom right corner, where here the first is 0 records, and so that means that we're just running the metric 0 shot without any domain-specific data. And here we can see that BLEURT with the synthetic pre-training is still robust. It still performs relatively well, but BLEURT, the lightest blue is when you don't pre-train and you also don't use WMT ratings, and you can see that as the lowest results. And it doesn't generalize well in 0 shot. When you do the pre-training and you subtract WMT, you still get decent results, but not kind of close to state of the art. You can see that BLEURT out of the box when it's trained on WMT is actually close to state of the art without any WebNLG data. And then as you increase the data, of course, then BLEURT can take advantage of that, and the other metrics don't. So the performance improves for BLEURT. And we can see that it's kind of getting state of the art with 800 records. Are there any quick questions about BLEURT? Otherwise, I'll spend the last 10 minutes on models. Yeah.
I had a quick question. So
yeah.
I was wondering, when you did the synthetic data pre-training, were all the metrics like normalized in the range 0 to 1? Because
yeah. So ToTTo does all kinds of normalization things and things like that. Yeah.
Okay. Yeah, because like for some kind of scores, I can imagine it'll be very skewed. Like you can't just do a linear normalization in some kind of metrics.
Yeah, there's also some weighting on certain groups. So the ones that are similar have a certain, because it's a multitask objective, right? So you have to weight the different tasks. Yeah.
Okay.
Yeah.
Thanks.
Okay. So the last thing I would like to talk about is models. And so this is work led by Ran Tian. And the idea is to have a learned confidence score that reduces hallucination. on noisy data. So here we have the source is this Wikipedia info box here. And we see that the reference, as we've seen before, has a lot of information that can't be entailed from the source, which we predict is one cause of hallucination. And here we see that the baseline hallucinates, which is a pointer generator model, it hallucinates that Franklin was a criminal defense attorney. And what we really like is that we just stop, right? Like there's no occupation given in the source. There's no reason that we should make up or hallucinate some occupation. And so we want to just say that, Franklin is an American and be done. And right now this looks very simple, but you can imagine that there's hallucination in the middle of the sentence, so that if you just kind of remove, you may result in something that's not fluent. So the intuition is that we want to look at different types of tokens and classify them in different ways. So our first token type is templatic words. And templatic words are things that do not convey source information, like born or these parentheses or is. And they're things that the model can just generate without looking at the source. So you can have an unconditioned language model. And given Michael Eric Dyson, given previous references, it's going to know that like born is something that it should say next, regardless of what the table says. And obviously, like it will know that it needs a period at the end of the sentence. On the other hand, the green is content words. And faithful content words, which are things that are supported by the table, require some sort of attention to the source. And things that are hallucinations are typically content words that are not closely associated with the source. So here, academic, author, and radio host is not supported by the source. So what we want is we want a confidence score at every position that is high if the token is either a templatic word, which is blue, or is supported by the source, which is green. And we want the confidence score to be low if it's not either of those. So if it's not a templatic word and it's not supported by the source, then it should have a low confidence. And there's obviously certain things that are a little bit fuzzy, like and is kind of fuzzy because grammatically, you need, it depends on American for and or things like that. So to determine if the word is templatic, we use an unconditioned base language model that basically is not conditioned on the source. To be simple, it's a little bit more complicated in the paper, but for simplicity, let's go with this. And then to determine if the word is supported by the source, we have a attention score. And the attention score is basically measuring how much the model is attending to the source at that time step. So here we've defined the decoder probability on the bottom left, y given the previous y is an x, and this is the softmax. Vt is kind of the output state, the hidden state at that position t, and ey of t is the embedding. And you're taking the dot product, and then you're taking the softmax to get the probability. And this Vt, or this nu of t, is a sum of two things. It's a sum of the attention vector, which is a weighted average of the source vectors with the attention weight, and ht, which is the LSTM decoder state. And basically, we believe that you have a high attention score if the AT norm is relatively larger than HT. Okay, so that's basically what's happening here. So when the attention score is high, it means that AT has a very high norm, so it has a high influence as to the model's output. Whereas when AT is low, it means that HT has a relatively higher influence to the model's output. And so now, we're going to say that the confidence score should be high if the token is either a templatic word, which is this blue term on the right, or it's supported by the source, which is this green term on the left. And the addition is kind of like an or. The challenging thing comes when, because this confidence score depends on learned parameters, AT depends on the decoder parameters, and this base language model also needs to be learned. We would like to train it jointly, and we would also like to be able to use it at inference time. So it's kind of a chicken and egg problem. If we knew the confidence score before training the other model parameters, then basically we could annotate all the data, all the references, and clean them to remove any unsupported phrases, right? So we could basically do the highlighting as we've shown. But the issue is that we're learning the confidence score while we're training the rest of the parameters. So this kind of naturally leads to some sort of EM or variational Bayes objective, where basically we do some sampling. So given a reference, we sample subsequences based on the confidence score in training. And then this updates the confidence score, and then we use that to resample, and it proceeds iteratively like that, as you would kind of do in the Bayesian probabilistic literature. And there's more details in the paper about that. And then in test time, so this alone will give you some gains, because the model will basically learn to ignore noisy references and train on clean data on its own in some way. We can do an additional thing to use the confidence score at test time once it's trained. This is based on a paper by Braverman et al. In 2018. You basically add one parameter model to the likelihood to recalibrate the output probabilities. So here, this SG is a stop gradient. So nothing that's this probability of this decoder probability or this confidence score are not being affected. The only learnable parameter here is kappa. Kappa is kind of reweighting the probability slightly, and it's reweighting it by the confidence score. And so it's just a test time maneuver. We have some experimental results on Wikibio and WebMLG, but I'll just show the Wikibio ones. In this talk, you can look at the WebMLG ones in the paper. And basically, we take two models, a pointer generator and a BLEURT encoder with an LSTM decoder, and we run them with and without the confidence decoding to see the difference. And then we also have some other models that people ran on Wikibio from the literature. And then our evaluation metrics are similar to before: BLUE, parent, and human eval. I think I'll mostly focus on human eval, and I'll also show how it relates to BLUE. And the parent results are in the paper. So what we see is that if we run a human eval, the confidence decoding significantly reduces the hallucination. So for instance, pointer generator is faithful 80% of the time, and the confident version of it is favorable 86.8% of the time. This comes with a degradation in BLUE, right? Because typically, to improve faithfulness, you also produce less words. So you will drop the BLUE because you will produce shorter sentences. So it penalizes the BLUE. We generally actually find that the models that have the highest BLUE hallucinate the most. So like structure aware is 45.4 BLUE, and it has 66.1% faithfulness. And we can also see a similar gain across BLEURT to LSTM. We see that BLEURT to LSTM is 75.6% faithful. Yeah, but once you make it confident, it's 79.4% faithful.
I have just a really quick question.
Yes.
Did you try removing the brevity penalty from BLUE and see, compare both of them to see if the scores were any different?
I have not. Yeah, that's actually a good idea. We did not remove the brevity penalty. It's possible that that would help, but I think then there's no. I mean, yeah, then you would have to have a separate recall measure, I guess. But yeah, that's a great point. We should have explored that. Fluency we find is generally similar across all the methods, at least in the vanilla form. We find that we do have a little bit of a reduction in coverage by using the confidence method, so there is a little bit of a precision recall trade-off. But you can force the coverage to be higher. So we can increase the coverage by using the length penalty. and that will make it have equal coverage to the baseline. But then you may lose some fluency, because if you kind of force the model to produce longer output, and it knows it still has to be faithful, then it has to sometimes trade off some things, so it sometimes trades off fluency. So this is kind of the summary. I talked about key works on each of these topics, and I welcome your feedback. This is the type of research we're continuing kind of in this little sub-team, kind of tackling hallucination from these 3 perspectives. And these are some links to resources and models and things like that. Thank you for your time. I'm happy to answer any questions.
That's awesome. Thank you so much, Ankur. Let's all unmute ourselves and thank the speaker before we go on to more questions.
Yeah, so I think going back to Nader's point, where he was asking if there's really clean, like the pre-trained BERT has data outside the training set. And I think you do see a little bit of this with the pointer in this Wikibio data set, right? Like we see that the pointer generator in this case is a little bit more faithful, even if it is, even if it has other weaknesses compared to the BERT model, because it's restricted only to the data that it sees. But you'll also see that the pre-trained model has considerably, I mean, at least on ToTTo, the output looks much better than pointer generator. But I think that's definitely a valid point.
Okay, so we have a lot of time for offline questions. So I guess we can get, so yeah, people can raise their hands or leave it on the chat. And I guess we can get started with one of the questions which were on the chat in the middle, which we didn't get to. So Prerna, do you want to unmute yourself and ask the question?
Yeah, sure. So in ToTTo, we see that in some of the examples, one particular thing that the model does not learn is how to infer the position of the record in the table.
Yes, let me back.
Yep. So here, like it is not able to infer last, and there was another example where it was not able to infer that there are 11 records. So if we are training a model on tables and then asking it to predict a sentence, isn't that a semantic that the model should be able to learn?
It should be, if it knows how to understand tables, right? So we did not use a very sophisticated table representation scheme. Like basically what I did was I took the cell, I had 2 ways of doing it. One way was I just linearized the whole table. And I kind of had some markers on which cells are highlighted. This technically is kind of information preserving, but the model doesn't seem to learn it very well. So that performed not very well, even if it's fully information preserving. The input format that worked better, even if it is not fully expressive, is I just took the highlighted cells and I concatenated them with the row column headers for each cell to localize them. And that limits the ability of the model to do reasoning. So I agree. In this case, it could not have said last, because I think I took this model prediction from the best performing model, and the best performing one doesn't know how to do inference. It doesn't, yeah. The worst performing ones technically can, but I generally didn't see it.
So does that mean that if we change the structure of our input, say we have more well-formed tables, the model might be able to learn the semantics based on table representations also?
Yes, I think if the table representation was better, then I think the model could learn these things in theory. Yes.
Okay.
I mean, I think that's an open research question. I'm not, yeah. I think it's an interesting research question. And yeah, I agree that it would be, maybe the community will have some filters to have certain subsets. The dev set is pretty large. It's like 7,500 examples. So even if there was a subset that had reasoning, it would hopefully be sizable.
Okay. I had a question about the third part of the talk, the modeling.
Yes.
So you mentioned at one point that it's a chicken and eggs problem to get these words, but I was wondering if you can like estimate that from the training data, because like template words will be more common if you aggregate all the references in the training data, and the green words you can directly like measure if they're copied from the source table or not. So yeah, I was wondering if you could like do like some sort of noisy synthetic annotation and then.
Yes. So I agree that you could do, I mean, it's not perfect, right? Like here, American is not in the table, but it's inferred from United States. So there's definitely some synonyms, but I agree that you could noisily annotate things and kind of get a more kind of a heuristic version, but less kind of a machine learning approach that might work well. I think there's a paper from someone from Zurich, from Katja Filipova. She does use these heuristics like what you're talking about. It's in MLFL. She uses these heuristics, and then she basically annotates each example on how much hallucination it has based on the word overlap, and then uses that as a control feature in the input of the model, which works pretty well. I think it's a short paper at MLFL to say, or in findings or something. But yeah, I think those are interesting approaches that might be good for Bootstrap. Even if they're not fully comprehensive, they might give some initialization to the model.
Okay, awesome. And the PBY unconditioned on X, that's a different model, right? That's trained jointly with the variational object.
Yeah, it's trained jointly. It's a separate model. It has some. It's unconditioned, but it has some odd dependence to the source that doesn't pass through the gradient for the model. If you read the paper.
Okay, awesome, cool. Okay, so yeah, we have time for questions. People can directly unmute themselves or leave it on the chat or raise their hands. Okay, so I don't see any more questions. So maybe we can wrap it up, and I guess people can reach out to you on email if they have.
Yeah, I mean, I think we're very, especially, yeah, I think we haven't released, like, I don't have much experience releasing resources and data sets that the community, so if people have questions or have suggestions for improvements, we'd be happy to get feedback.
Okay, awesome. So let's unmute ourselves once again and thank Ankur. Okay, so I will stop the recording.